Welcome to this lecture on Solution to Exercise 5.4, Question 1 to Question 8 from the book Introduction to Real Analysis by Bartle and Sherbert.
Welcome everyone to this lecture series. Today we will solve exercise for section 5.4 from the book Introduction to Real Analysis by Bartle and Sherbert. So in this video this is part 1 of the solution series, and in this video we will solve from question 1 to question 8. So let us start with the question number 1. This is the question number 1. So in this we are given the function fx equal to 1 by x, and we have to show that it is uniformly continuous on the set a equal to a to infinity, where a is a positive constant. We have to show that fx equal to 1 by x is uniformly continuous on the set a. So to show that f is uniformly continuous, we will have to take any arbitrary epsilon, and then we will have to find some delta such that fx minus fy is less than epsilon whenever we take x minus y to be less than delta. So let us start with any arbitrary epsilon. So let epsilon greater than 0 be any real number. So then consider for any xy belonging to a which is equal to a to infinity. So we are starting with any xy. We are considering fx minus fy. So this is nothing but 1 by x minus 1 by y. So this is nothing but 1 by xy x minus y. We can write it like xy because x and y both are positive, because a is positive, a is greater than 0. Now we want this to be less than equal to some, so we want to reduce this, make this independent of x. So what we will do, because both x and y are greater than a, so when we will replace this, then we will get this 1 by a square x minus y, because we have to increase the number. To increase the number we have to reduce the denominator, and we can because both x and y are greater than a, so we can reduce x and y by a. So what delta we can choose? We can choose delta equal to, let delta equal to epsilon a square greater than 0. Then clearly by the choice of delta, it is evident that fx minus fy is less than epsilon whenever our x minus y is less than delta. Hence, by definition of uniform continuity, f is uniformly continuous on 0 a to. So for any positive integer a, the function fx equal to 1 by x is uniformly continuous on the interval a to infinity. So this completes the proof of question number 1. Now let us move to the question number 2. So in question number 2, we are given the function fx equal to 1 by x square, and we have to show that it is uniformly continuous on the interval 1 to infinity, and it is not uniformly continuous on the interval 0 to infinity. So again we will proceed as in the first question. So we will start with any epsilon greater than 0. So let epsilon greater than 0 be any real number. Now for any xy belonging to 1 to infinity, consider the difference, consider fx minus fy. So this is equal to 1 by x square minus 1 by y square. So on simplification, because both x square and y square are positive, so we can remove the modulus sign. So this is this. Now this can be written as x plus y, x minus y upon x square y square. Now we can use the triangle. In fact, this is still equal to, now we can use the triangle inequality to get this, and both x and y are positive, so we can remove the modulus sign. So this is x plus y upon x square plus y square x minus y, and this can be written as, in fact it is still equal, sorry, this is plus, now this is x y square plus 1 by x square y x minus y. Now when we will because both x and y are greater than equal to 1, so when we will replace x and y by 1, then number will increase because they are in denominator. So when we decrease the denominator, the number increases. So this is 1 by 1 plus 1 by 1. We are replacing x and y by 1. Since our xy is greater than equal to 1, so we are decreasing the denominator, so number will increase. This is equal to 2 times x minus 5. So delta we should choose. So let delta equal to epsilon by 2 greater than 0. Then by the choice of delta, it is evident that fx minus fy is less than epsilon whenever our x minus y is less than delta. Hence, by definition of uniform continuity, f is uniformly continuous on 1 to infinity. Now we proceed to the claim 2. So we now proceed to the claim 2. Claim 2 is that f is not uniformly continuous on 0 to infinity. So it was uniformly continuous on 1 to infinity, because in fact one can show that it is uniformly continuous on any interval a to infinity where a is positive, but it is not uniformly continuous on 0 to infinity. So we will have to take one sequence. So we will use the non-uniform continuity criteria. So we will take two sequences xn and yn, such that their difference converges to 0, but the corresponding difference of images, they are greater than some epsilon naught. So epsilon naught we will take equal to half. So let epsilon naught equal to half greater than 0. Let xn equal to, for each n belonging to n, let xn equal to 1 by n, yn equal to 1 by n plus 1. Then clearly, then xn minus yn is equal to 1 by n minus 1 by n plus 1, which is equal to 1 by n times n plus 1, so which converges to 0 as n approaches infinity. Also, f of xn minus f of yn is equal to 1 by n square minus 1 by n plus 1 whole square, sorry, n square minus, because fx is 1 by n square, this is 1 by xn square minus 1 by yn square, so which is equal to n square minus n plus 1 whole square. So this is nothing but your 2n plus 1 into 1. We are using the formula a minus 1, a minus b, a plus b, so we are getting this minus 1. So this is equal to 2n plus 1, which is greater than epsilon naught, which is equal to half. So hence by non-uniform, so we are able to find two sequences which satisfy the condition of non-uniform continuity criteria. By non-uniform continuity criteria, f is not uniformly continuous on 0 to, so any interval containing 0 will the function will not be uniformly continuous on that, but if we take any interval with a to infinity where a is positive, then the function will be uniformly continuous. Now let us move to the question number 3. So it is again based on non-uniform continuity criteria. So we are given two functions f and g. We have to show that both are not uniformly continuous on the given intervals. So solution A, so we We have to show that fx equal to x square is not uniformly continuous on the interval 0 to infinity. So we have to take the non-uniform continuity criteria. So for this, again we will take let epsilon naught equal to half greater than 0 for each n belonging to n. We let xn equal to root n and yn equal to root n plus 1. So then for this choice of xn and yn, it is easy to see that consider for all n belonging to n, xn minus yn is equal to root n minus root n plus 1. Then upon rationalization, what you get is root n plus root n plus 1 n minus n plus 1. So this is, so basically we have multiplied and divide, and then we have used the formula a square minus b square is equal to a minus b, a plus b. So you get this. So this is equal to 1 by root n plus root n plus 1, which converges to 0 as n approaches t. Also, for all n belonging to n, your fxn minus fyn is equal to n minus n plus 1, which is equal to 1, which is greater than epsilon naught, which is equal to half. Hence, by non-uniform continuity criteria, f is not uniformly continuous on f is not uniformly continuous on 0 to infinity. In fact, instead of taking 0 to infinity, we could have any interval a to infinity, and we could have still shown that f is not uniformly continuous on that interval, because for to choose this xn and yn, because we are choosing xn equal to root n and yn equal to root n plus 1, this is only possible whenever whenever domain is unbounded. If the domain is bounded, then we cannot choose such a sequence, because this sequences and they both the sequences are unbounded sequences. So our domain has to be unbounded. So the function is not uniformly continuous on any unbounded interval. Now 3b, so b part, so gx is equal to sine 1 by x on 0 to infinity. So we have to show that it is not uniformly continuous on 0 to infinity. So again, we can easily show the same way that we have shown that this is not continuous at 0. So on the same lines, we can show that it is not uniformly continuous on the interval 0 to infinity. So we will take the t, so let epsilon naught equal to 1 by 2 greater than 0 for each n belonging to n. Let n equal to 1 by 2n pi. So same which we took in while showing that this the function sine 1 by x is not uniformly continuous, and yn equal to 1 by 2n pi plus pi by 2 for all n belonging to n. So then clearly, then for all n belonging to n, your xn minus yn is nothing but 1 by 2n pi minus 1 by 2n pi plus pi by 2, which is equal to, so when you will simplify this, you will get pi by 2 upon 2n pi plus pi by 2, which clearly goes to 0 as your n approaches to infinity. So xn minus yn converges to 0 as n approaches to infinity. Now consider, so also for all n belonging to n, f of, so g of xn, so g of xn minus g of yn is equal to sine 1 by xn minus sine 1 by yn, so which is nothing but sine 2n pi minus sine 2n pi plus pi by 2. Sine 2n pi is your 0, while sine 2n pi plus pi by 2 is 1. So it happens to be equal to 1, which is greater than epsilon naught, which is equal to half. Hence, by non-uniform continuity criteria, f is not uniformly continuous. sorry, G is not uniformly continuous on G is not uniformly continuous on 0 to infinity. Hence proved. We have completed question number 3. Now let us move to question number 4. In question number 4, we are given the function fx equal to 1 upon 1 plus x square. We have to show that it is uniformly continuous on the whole real line R. So let us start. So we have to show that it is uniformly continuous on the whole real line R. So for that we will consider any epsilon greater than 0. So let epsilon greater than 0 be any real number. Let epsilon greater than 0 be any real number. Now for any xy belonging to R, consider fx minus fy. This is nothing but 1 upon 1 plus x square upon 1 plus y square. So when you will simplify it, so you get 1 plus x square 1 plus y square upon x square minus y square. So on simplification you get x plus y, x minus y upon 1 plus x square 1 plus y square. So in the numerator we can apply the triangle inequality. So this is less than equal to mod x times mod y upon 1 plus x square 1 plus y square x minus y. So this is less than equal to mod x times. So now we are splitting it and we are removing this term, one term from it. So we are getting this. So what we have done basically is that because mod x by 1 plus x square 1 plus y square is less than equal to mod x by 1 plus x square, because replacing this by 1 means we are decreasing the denominator. So when you decrease the denominator, the number increases. So we have got this. Now this term is less than 1 by 2, this term is less than 1 by 2, or you can simply say because this is 1 plus x square, so if x is lying between minus 1 to 1, so this is smaller than 1, so this is greater than 1, so your numerator is smaller than denominator, so this number is less than 1. If your x is greater than 1, then x square is greater than mod x, so again this number is numerator is smaller than denominator. So in either case numerator is smaller than denominator. This is less than equal to 1 plus 1 times x minus y. Since mod x upon 1 plus x square is less than 1 for all x belonging to R. In fact, one can easily prove that mod x upon 1 plus x square is less than 1 by 2. This you can show by considering the difference 1 by x minus 1 by 2. So this, when you will simplify it, you will get this 2x minus 1 minus x square upon 2 times 1 plus x square. Now this will become, this is equal to minus 1 upon x plus minus 1 by whole square to 1 plus x square. So this is a negative term, so this is smaller than this. So one can easily show this, but we don't need this exact inequality. We can work with 1. So it's simple to have to conclude that this is smaller than 1. So we have this. So this is less than equal to less than 2 times x minus y. In fact, here we will have equality. So 2 times x minus y. So let delta equal to epsilon by 2 greater than 0. Then by the choice of delta, it is evident that fx minus fy is less than epsilon whenever our x minus y is less than delta. Hence, f is uniformly continuous on the real line R. F is uniformly continuous on the real line R. Now let us take the question number 5. So question number 5 says that sum of two uniformly continuous function is again a uniformly continuous function. So we have to prove that sum of two uniformly continuous function is a uniformly continuous function. So for this we will start with, again we have to show f plus g is uniformly continuous on A. So we will start with any epsilon greater than 0. So let epsilon greater than 0 be any real number. Now since f is uniformly continuous on A, so there exists delta 1 greater than 0 such that fx minus fy is less than epsilon by 2 whenever our x minus y is less than delta 1. Mark it as A. Now again, as g is uniformly continuous on A, so there exists delta 2 greater than 0 such that gx minus gy is less than epsilon by 2 whenever x minus y is less than delta 2. Mark it as B. Now we want A and B to hold together for the same delta, so we will take let delta equal to minimum of delta 1 delta 2 greater than 0, then fx minus fy is less than epsilon by 2 and gx minus gy is also less than epsilon by 2 whenever our x minus y is less than delta. So mark it as star. So we are going to use this. So now consider for any xy belonging to A with x minus y less than delta, f plus dx minus f plus dy. So this is nothing but this is your fx plus gx minus fy minus dy. So by using triangle inequality we get this fx minus fy plus gx minus dy, and this is less than epsilon by 2 plus epsilon by 2 using star, which is equal to epsilon. So hence by definition of uniform continuity, f plus g is uniformly continuous on A. We are able to prove that if sum of two continuous uniformly continuous function is again a uniformly continuous function. So let us move to the next question, which is question number 6. So in this question we are asked to show that if two functions are uniformly continuous and they are bounded on their domain, then their product is also uniformly continuous. We are given two uniformly continuous function f and g on A, and we are also given that they are bounded on A. So we have to show that their product fg is uniformly continuous on A. So let us start. So given f and g are uniformly continuous on A, and second, f and g are bounded on A. To show fg is uniformly continuous on A. So for this we will start with any epsilon greater than 0. So let epsilon greater than 0 be any real number. Now since f g are bounded on A, so there exist m1 and m2 belonging to are positive, so there exist two positive real numbers m1 m2 such that mod fx is less than equal to m1 and mod gx is less than equal to m2 for all x belonging to A. Mark it as star. So we have found two bounds m1 and m2 corresponding to f and g. Now consider for any xy belonging to A, fgx minus fgy. So we will approach the same way we approached for the continuity. So this is nothing but fx gx minus fy gy. Now we want to separate them. So how can we separate? We will take the mixed form. So we will take one with x and one with y. So we will take fx gy, or one can take fy gx. So we will add and subtract this term fx gy. Now on simplification, it is easy to see that you will get this mod fx. You simplify and use a triangle inequality, you get this, and here you get mod gy mod fx minus fy. So now we can replace again this fx by m1, this gy by m2 using star. So this is m1 times gx minus gy plus m2 times fx minus fy using star. So we have used star here. So mark it as double star. So this is our double star. So this is our double star. Now we proceed. Now since f is uniformly continuous on A, so for above epsilon greater than 0, there exists delta 1 greater than 0 such that fx minus fy is less than epsilon times 2m2. Why we are taking 2m2? Because we want to use this in star and we want to replace this. So when we will replace this by epsilon by 2m2, then it will become epsilon by 2. So and similarly we will take this to be less than epsilon by 2m1. So overall we will get epsilon. That's why we are taking this to be less than epsilon by 2m2 whenever x minus y is less than delta 1. Also, as g is uniformly continuous on A, so there exists delta 2 greater than 0 such that gx minus gy is less than epsilon times 2m1 whenever x minus y is less than delta 2. So using, let delta equal to minimum of delta 1 delta 2, then fx minus fy is less than epsilon times 2m2 and gx minus gy is less than epsilon times 2m1 whenever our x minus y is less than delta. So mark it as double star or triple star. Using triple star in double star, we get f plus gx minus f plus gy is less than m1 times epsilon by 2m1 plus m2 times epsilon by 2m2, which is less than epsilon whenever x minus y is less than delta. Hence by definition of continuity, hence by definition of uniform continuity, f plus g sorry, fg, we are considering the product here. So this is your fg, we are talking about the product here. So fg, this is your, so by definition of uniform continuity, fg is uniformly continuous on A. So we are able to prove question number 6. Now we will proceed to question number 7. So we have shown that in question number 6, we have shown that product of two uniformly continuous function is uniformly continuous function provided the they both are bounded on their domain. We have shown, so here we have shown that if f and g are two uniformly continuous function on their domain and they are bounded on their domain, then their product is also uniformly continuous. But if we drop the condition of boundedness, then we will see that the product may fail to be uniformly continuous, although the functions are uniformly continuous on their domain. So this is what we are going to prove in question number 7. So in question number 7, we are given two functions, fx equal to x and gx equal to sin x. We have to show that although they both are uniformly continuous on their domain, but their product is not uniformly continuous on real line R. And you can easily see that the function fx equal to x is not bounded on R. So we have dropped the condition of boundedness on the domain, and we are able to see that product may fail to be uniformly continuous on R. So this is what we are going to prove. So claim 1, fx equal to x is uniformly continuous on R. So start with any arbitrary epsilon. So let epsilon greater than 0 be any real number. So in this case, we know that delta we will have to take if equal to epsilon. So consider for any xy belonging to R, fx minus fy is equal to x minus y. So we will have to take delta equal to, so let delta equal to epsilon greater than 0, then by the choice of delta, it is evident that fx minus fy is less than epsilon whenever our x minus y is less than delta. Hence, by definition of uniform continuity, f is uniformly continuous on R. So we are able to prove that f is uniformly continuous on R. So claim 1 is proved. Now we will prove the claim 2. So claim 2, we will prove that fx equal to sin x is uniformly continuous on fx equal to sin x is uniformly continuous on R. So for this, what we will do, we will take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we have started with any arbitrary epsilon. Consider for any xy belonging to R. So we have started with any arbitrary epsilon, and we have taken any 2 points in R. Consider gx minus gy. So this was our function gx, not fx. This was gx. We started with gx minus gy. So this is sin x minus sin y. So now we will use the formula of sin a minus sin b. So this is 2 cos x plus y by 2 sin x minus y by, now this is nothing but this is less than equal to, so this is 2 times cos x plus y by 2 sin x minus y by 2. So here we will use this is less than equal to 1. So this we will replace by 1, and this we will replace by mod x minus y by 2. So this is less than equal to 2 times x minus y by 2. So we have used two inequalities. First, cos theta is less than equal to 1 for all theta, and second, we have shown that sin x is less than equal to mod x for all x belonging to R. And this result you can prove by proving that minus 1 is less than equal to sin x by x less than equal to 1. So using this, then you multiply by x on both sides, so you will get this result. This can reduce easily this result from this result. So we get this. Now this is equal to x minus y, so we have to take, so let delta equal to epsilon greater than 0. Then by the choice of delta, it is clear that fx equal to, so it is clear that gx minus gy is less than epsilon whenever our x minus y is less than delta. Hence g is uniformly continuous on R. So we have shown that fx equal to x is uniformly continuous on R, and we have also shown that gx equal to sin x is uniformly continuous on R. Now we have to show that their product is not uniformly continuous on R. So we will have to take two sequences xn and yn such that the difference converges to 0, but the corresponding fgxn minus fgyn should be greater than equal to epsilon naught for some epsilon naught greater than 0. So claim 3, fgx equal to x sin x is not uniformly continuous on R. So we will have to take two sequences. So we will take, so let epsilon naught equal to 1. So or we can take 1 by 2 for on to be on the safer side greater than 0, and for each n belonging to n, let xn equal to, we will take xn equal to 2n pi and yn equal to 2n pi plus 1 by n. So this is what sequence you have to take. You have to take xn equal to 2n pi, yn equal to 2n pi plus 1 by n. Then for each n belonging to n, xn minus yn is equal to 2n pi minus 2n pi plus 1 by n, which is equal to 1 by n, which converges to 0 as n approaches infinity. So this xn minus yn converges to 0 as n approaches to infinity. Also for all n belonging to n, f of fg xn minus fg yn is equal to fxn gxn minus fyn gyn, which is equal to 2n pi sin 2n pi minus 2n pi plus 1 by n sin 2n pi plus 1 by n. So because sin 2n pi is 0, so this whole will become 0, so we will be left with this. So we will be left with minus 2n pi plus 1 by n, and sin 2n pi plus 1 by n will be sin 1 by n, because sin 2n pi plus theta is sin theta. So this is sin 1 by n. Now this is equal to 2n pi plus 1 by n. Again this is equal to sin 1 by n. Now because we want it to be greater than epsilon naught, so we cannot replace this by 1 by n, so we will have to replace this by something small. bigger. So for smaller, something smaller, because we want to prove it for greater than 1 by 2. So for this we will use the fact that since limit x tends to 0, since limit x tends to 0, sin x by x is equal to 1. So this implies sin x by x, because this limit is going to 0. So for epsilon equal to 1 by 2, there exists delta greater than 0 such that sin x by x minus 1 is less than 1 by 2 whenever x minus 0 is less than delta. So this implies, so when you will simplify it, you will get this: sin x by x is less than so this is less than 1 by 2 is less than sin x by x is less than 3 by 2 whenever your mod x is less than delta. Now if we take x, because our 1 by n is positive, so we want to have this positive. So what we can do is, so whenever, so this implies sin x by x is greater than 1 by 2 whenever our x 0 is less than x less than delta. 0 is less than x less than delta. Now because we have taken x to be less than delta, so this will imply, that so because now x is we have taken x to be positive, so this is sin x is greater than x by 2 whenever 0 is less than x less than delta. Now for by Archimedean property we can find m, sufficiently large m, such that 1 by m is less than delta. So using this in this, so using double star, so by Archimedean property, there exists m belonging to z positive such that 1 by m is less than delta. So hence sin 1 by n is greater than, because we are taking x to be equal to 1 by n in this, so 1 by 2n for all n greater than equal to m. So using this, and this is greater than 0, so using star in double star, we get xn minus fyn is greater than 2n pi plus 1 by n times 1 by 2n. So this is equal to, so we have replaced sin 1 by n by 1 by 2n. So this is, when you will simplify it, you will get pi plus 1 by 2n square, which is greater than pi, which is greater than 1 by 2, which is equal to epsilon naught for all n greater than equal to m. True for all n greater than equal to m. Hence by non-uniform criteria, form continuity criteria, f is fg, this one is fg product, this one is your fg of xn minus fg of yn. Fg is not uniformly continuous on R. What you could have done is, you could have directly shown that this, from star you could have directly concluded that fg is not uniformly continuous, because you could have shown that this is diverging to infinity. So once this diverges to infinity, so it follows the path of non-uniform continuity criteria. So you could have directly also concluded, so instead of showing all this, you could have directly concluded that because this converges to infinity, so when you will take n to infinity, so this will go to infinity, this will go to 0, and this lies between -1 and 1, so overall this will go to infinity. We could have directly concluded from here that this, because this converges to infinity as n tends to infinity, so the function is not uniformly continuous, because for a function to be uniformly continuous, the distance between 2 points, the distance, if the distance between 2 points are small, then their distance between their images should also be small. But here we are seeing that the distance between the images is diverging to infinity. So from here also we could have concluded that the function is not uniformly continuous. Okay, now let us move to the next question, which is question number 8 and the last question of this part. So here we are given two uniformly continuous function, and we have to show that their composition is also a uniformly continuous function. So again the proof will follow on the lines of continuity, where we have shown that composition of two uniformly continuous function is uniformly continuous. So solution, let us start. So let epsilon greater than 0 be any real number. So first we will use the continuity, because we have to show that f of j is continuous. So first we will use the continuity of uniform continuity of f, then we will use the uniform continuity of g. Since f is uniformly continuous on R, so there exists delta star greater than 0 such that f of u minus f of v is less than epsilon whenever u minus v is less than delta star. So mark it as A. Again, as G is uniformly continuous on R, so instead of epsilon, now we will take this delta star. So for delta star greater than 0, there exists delta greater than 0 such that we are replacing epsilon by delta star in the uniform continuity definition. So we get gx minus gy is less than delta star whenever our x minus y is less than delta. So mark it as B. Now for any xy belonging to R with x minus y less than delta, so from B we will have, so gx minus gy is less than delta star using B. Now because gx and gy satisfy this condition of A, if we take gx, u equal to gx and v equal to gy, then this condition is satisfied. So from A it follows that f of gx, so instead of u we are taking gx, and instead of v we are taking gy, because gx and gy is satisfying the condition of A. So this is less than epsilon using, that is, f of gx minus f of gy is less than epsilon whenever x minus y is less than delta. Hence by definition of uniform continuity, hence by definition of uniform continuity, f of g is uniformly continuous on. This completes the proof of question number 8, and hence also our part 1 of this solution series of exercise 5.14. So now in the next video we will solve from question number 9 till question number 16. Till then, have a good day. Bye everyone.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning to Cosmos Learning. To watch more, click on any of these cards. Thank you once again.